So the speaker today is Aditya Hebbar, and the talk is on spinning S-matrix bootstrap in 4D. All right, go ahead.
Yeah. So yeah, I'd like to thank the organizers for giving me the opportunity to talk. So this talk will be based on this paper, which we put out last week, and this was with Dennis and Joao. The outline for the talk, I'll give a brief introduction to S-matrix bootstrap, and then I'll do a lightning review of the scalar S-matrix bootstrap, which was something that it's basically a recap of a paper which came out three years ago. After that, I will talk about the general formalism to generalize the scalar S-matrix bootstrap to particles with spin. So we'll just set up the machinery for particles of any spin. And then as an application, we'll consider the next simplest case after scalars, which is Majorana fermions, identical. And then we'll be able to bound some couplings for these first scattering of these identical Majorana fermions. And then I'll conclude. So the S-matrix bootstrap is an old idea, so it's from the 60s, but it was recently revived, inspired by the success of the conformal bootstrap. And the idea is similar, so we want to use analyticity, crossing, and unitarity to constrain the space of QFTs. And it's already quite successful in 2D, so integrable theories have been found on the boundary of allowed space of QFTs. In 4D, okay, we're still searching for such an example. And another thing about S-matrix bootstrap in 4D is that all prior works have dealt with scalars. So with this work, we would like to generalize to spinning particles. And this way we'll be able to study some phenomenologically interesting cases, such as say pion-nucleon scattering or say glue balls. So yeah, this is the motivation for our work. And now I'll do a brief recap of scalar S-matrix bootstrap. So the idea is that, okay, we consider 2-to-2 scattering of identical scalar particles. And then we define the amplitude as the matrix element of the scattering operator in between two incoming and outgoing states. And the identity, we remove the identity, which is the piece due to free propagation of the particles. And then the T operator, or the matrix element of the T operator, encodes the dynamics. And here we've written it as a function of S, T, and U, which are called Mandelstam variables or Mandelstam invariants. And they're defined as follows. So S is the energy in the center of mass frame, and T is called the momentum transfer. And usually we define another variable called U, and only two of these are independent because there's this constraint which says S plus T plus U is 4m squared. When we consider scattering of identical scalar particles, the scattering amplitude is totally symmetric under the interchange of arguments. For analyticity, what was assumed was that it's Landau analyticity. So the scalars being scattered are the lightest particles in the theory. So if you just look at the Landau diagrams, the only non-analyticities are, say, a possible bound state between 0 and 4m squared, and then multi-particle cuts that start from S equals 4m squared. So this is the crossing and analyticity property of the scalar scattering amplitude. And then to impose unitarity, you need to make these things called partial waves. So they are defined as follows here. So you have to integrate over the scattering angle with this Legendre polynomial. And then basically what unitarity tells you is that for any integer spin L, this partial wave should be bounded by 1 in modulus for S greater than 4m squared. So the idea was to write an ansatz which is manifestly crossing symmetric and had the right analyticity properties. And then after that, the idea was to impose unitarity as a semi-definite positivity constraint. So this condition that the partial wave has modulus less than 1, you can write it as this positivity of this matrix. And this way you can implement it on a computer using, for example, STPB. And by doing this, these authors were able to get some beautiful bounds. For example, they were able to get this bound on cubic coupling to another scalar. And now what we would like to do is to repeat all this for at least set up the formalism to repeat all this for particles of any spin. And now I'll just provide an overview, so a short overview of how
Aditya, can I ask a question?
Yeah.
So there was recently some critique from which Sasha Zhibredov told us in his talk that this condition cannot be imposed in the answers because point-wise it's not true, blah, blah, blah.
Yeah.
Do you have anything to say about this?
No, in this we don't have anything to say. So I think they're trying to implement their ideas. So I think we are also waiting for that and then maybe we can generalize to spinning particles, but we don't have anything more to say about that. So we still impose point-wise.
Okay, thanks.
Okay, so so now before I dwell into the details for the spinning case, I just want to provide an overview of what changes in each of the points that I mentioned. So first of all, it's a straightforward fact that now since I have each of the particles have spin, I just don't have one function. I have multiple functions. So for example, particle 1 could take many different helicities. So for example, it has 2j plus 1 number of choices for its helicity. And similarly for particles 2, 3, and 4. So in general, if you don't impose any additional symmetry conditions, you have these many number of functions. Then for analyticity, it turns out there are some singularities in the S and T planes, which are purely kinematic in nature, but we can isolate them and regularize them. And once we do that, we assume that these satisfy Landau analyticity. Then crossing, okay, once again, you have a bunch of amplitudes. So it's going to be a matrix equation now, which links S channel amplitude to the T channel amplitude. And this matrix also turns out it depends on S and T. So it's not just purely numerical. And lastly, unitarity also is going to be a matrix equation. So here, this one here is a matrix, and this S also is a matrix with all these partial amplitudes. So this is just an overview of what is to come. And now, if there are no questions, I'll go into the details. Okay. So we have to start from the basics. So I start with the Poincare reps, and in particular, we'll be working with the helicity basis for particle states. We label them by this quantity C, which is basically the eigenvalue of the Casimir operator, and P is the momentum, 3 momentum. So there is a relation between the 3 momentum, and L is the total spin, and lambda is the helicity. And under Lorentz transformation, the point is that we assign, so suppose you do a Lorentz transformation lambda, then there is a rotation that is associated to this transformation, and this rotation also depends on the momentum, and this is called a Wigner rotation. And what happens basically is that the state with helicity lambda, you see it's a linear combination of all the other helicities, and the coefficients are given by this object called the Wigner D matrix. And this is precisely the object you find in when you consider rotations in spin L representations of SU2. So this is exactly that. And why we like helicity basis is that for the case where this Lorentz transformation is a rotation, this rule simplifies, and this Wigner D matrix just becomes a phase, which means that basically the helicity is unchanged by rotations. But obviously helicity changes is not Lorentz invariance, but it is invariant under rotations, and this is convenient for us, and that's why we choose to use the helicity basis. Okay. A special class of these irreps are one particle states. And in that case, we identify this C that I introduced in the previous slide with the mass of the particle. And then we also use the notation J for intrinsic spin, and L is total spin. And how we distinguish a one particle state is that we say that this label M is discrete. So we assume that, okay, we have a discretum of particles, so there is no continuum of particles, and that's how you distinguish, say, one particle states from these general Wigner-Irrefs. So in the last slide, I talked about the Lorentz transformation properties. Under parity, the momentum changes to the diametrically opposite momentum, and helicity also changes sign. And this we can understand physically, because helicity intuitively is the projection of the total spill along the direction of momentum. And now you see under parity, the angular momentum direction remains the same, whereas momentum changes direction. So the projection goes to minus of itself. And that's the physical reason why helicity changes sign. And this phase, okay, to get this phase, you have to do some algebra where you have to commute this P operator with the Lorentz generators. Similarly, for time reversal, again, momentum changes direction, but this time angular momentum also changes direction. So you expect that the projection remains the same, and that is why helicity is it remains the same under time reversal. Okay, and now now that we've studied a bit of the one particle states, we can introduce the scattering amplitude. So we write the S operator as the free propagation piece plus the T operator, which encodes the dynamics. And then we consider two particle states. So they're just tensor products of one particle states. And then scattering amplitudes, you just take matrix elements of the T operator in these two particle states. And the Lorentz transformation property of the amplitudes, it follows directly from the transformation of the one particle states. So the incoming states, they are the kets, so they just transform with this Wigner-D matrix. And the outgoing states are the brass, so they transform in the conjugated with the conjugated D matrix. And this is so this is how we deduce the Lorentz transformation property of the amplitudes. And these amplitudes, as you can see, are functions of the four momenta. So in the literature, they are sometimes called generalized helicity amplitudes. And now we want to define quantities which are functions of the Mandelstam invariance, because here these things, okay, they still transform. So we have to do a bit more work to define quantities that are functions of the Mandelstam invariance. So for that, there are two options. So option one is to define tensor structures. So here the tensor structures are indicated with bold T. And the idea is that they encode all the Lorentz transformation property of the tensor structure, the Lorentz transformation property of the amplitude, so that these scalar components are don't transform under Lorentz transformations. The other option is that you pick a special frame. So we are going to pick something called the center of mass frame, and just define the function of Mandelstam invariance in this special frame. And this is unambiguous because in any other frame, it's well defined through this transformation property. So if you want to know the amplitude in any other frame, you just take the amplitude in the center of mass frame, you know it as a function of st and u, then you just boost to your new frame, and the transformation law gives you its value in the new frame. So this second option is basically similar to the conformal frame that is used for spinning correlators in CFT, whereas the first option is like the covariant approach or the embedding frame approach. And for the most part, I'll focus on the second option. So now I want to give more details of the center of mass frame. So in picture, it's just like this. So particle 1 is along the positive z-axis, and particle 2 is along the negative z-axis. Particle 3 is at an angle theta with respect to the z-axis, and particle 4 is opposite it. And we keep all these four particles in the xz plane. And this is the definition of the center of mass frame. In terms of equations, so as indicated by the picture, the particle 1 and 2 are along the z-axis, and particles 3 and 4 are at some angle theta with respect to the axis. And now we can write all these parameters, so the energies and the momenta and the angles in terms of the Mandelstam variables. And in general, if you want to write them for some unequal masses, the expressions are cumbersome. So here I've only shown the expressions for the equal mass case where it's much easier to write, for example, on a slide. And yeah, so the energy is basically the square root of S, and the momentum goes like a square root of S minus 4m square over 2, and so on. And the main point is that now if you notice, in the S and T variables, you see that these relations are not analytic, in particular at S equals 0 or T equals 0 or U equals 0, and also at S equals 4m squared, there is some non-analytic behavior. And this is in fact going to be the cause for these kinematic singularities that I mentioned before. But in general, so we can actually figure out the general kinematic singularities for, say, generic spin. But in the talk, I won't have time to do that. So I'll just mention it briefly for the Majorana fermion case, but I won't talk any more about the kinematic singularities for the general spin case. So now we come to crossing. And the first point is that, so what is crossing? So when we want to do crossing, we imagine we have, say, two processes. So the process 1, 2 goes to 3, 4, and the process 1, 3 bar goes to 2 bar 4. And then the idea is, like, suppose I take this amplitude and then I analytically continue it, which was, so the amplitudes are defined as functions of momenta, and the momenta should have positive energy. But I can imagine that I analytically continue it to complex momenta, and through some path, I arrive at negative energy momenta. And then crossing basically tells us, is basically the statement that is that this amplitude evaluated at negative energies is essentially the crossed amplitude for positive energy, so the physical crossed amplitude. For the spinning case, immediately the question arises, you have many choices for, say, the S channel amplitude and many choices for the T channel amplitude. So which one crosses to which? And historically, the way people deduced this was by comparing the Lorentz transformation properties. So the left-hand side transforms in a particular way and the right-hand side transforms in a particular way. And now I have to analytically continue this Lorentz transformation because the transformation is defined only for positive energy momenta. And so I have to analytically continue it to negative momenta. Basically what I mean is, as I mentioned before, this Wigner-D matrix that is associated to this Lorentz transformation, it depends on both the Lorentz transformation and the momenta. And now I'm analytically continuing in this momentum. And for a particular choice of this path of analytic continuation, it turns out that this Wigner matrix with momentum minus p is basically the Wigner matrix conjugated for the positive momenta. So and you also see that the helicities changes sign. The fact that the Wigner matrix is conjugated is good because we know that when I go to negative momenta, I want an incoming particle to become an outgoing particle and an outgoing particle to become an incoming particle. So this changes this transformation property is what we would expect. I mean, this relation is what we would expect from this transformation property. But it also turns out that the helicity changes sign. So now if we just use this relation and compare the Lorentz transformation properties, we can conclude that the S channel amplitude is basically the T channel amplitude with flipped helicities, but up to some overall helicity independent phase, which we can't really fix using this argument, because if you just multiply by some, say, -1, the transformation properties still remain the same. So the way to fix this phase, for one way would be, for example, to use LSZ. Or another way is that you can do some perturbative computation and then try to fix it. Now we have the crossing relation for the generalized helicity amplitudes. So for the
question, Aditya.
Yeah.
If you need to invoke LSZ for the last step, wouldn't LSZ give you everything?
Yeah. So here Yeah, right. So if you invoke LSZ, yeah, you can basically get everything except that, yeah, so you have to think about what's happening for these generalized spinner, the generalized solutions that you define for like, so what I mean is that you have, so in the LSZ, you need these wave function solutions, right? To go from the correlation function to the S matrix element. So yeah, if you can figure out how they analytically continue, then yeah, indeed LSC just gives everything. Yeah. So in some sense, this is just some bit of archaeology we're showing how this was done. But this argument, for example, it works for any J, and in the, yeah, this phase, yeah, it doesn't fix. Yeah.
Thanks.
Okay. So now we have the crossing relation for the functions of the four momenta. And now we want to go to the center of mass frame where we can define functions of the Mandelstam invariants. But the problem is, if suppose I put, say, the left-hand side in its center of mass frame, once I cross, the right-hand side is not going to be in the T-channel center of mass frame. So what I need to do is is an intermediate step. So I need to boost before I cross so that I can end up in the T-channel center of mass frame. In pictures, it's like this. So I start in the S-channel center of mass frame. So the process is 1, 2 goes to 3, 4. So I have 1 and 2 along the Z-axis and 3 and 4 at an angle theta. So the first step I do is to do a Lorentz transformation. And it turns out that this Lorentz transformation is going to be complex in general. And what I need to do is align particles 1 and 3 along the Z-axis and particles 2 and 4 along this, minus theta with respect to the Z-axis. And now so here it's still the process 1, 2 goes to 3, 4, but it's not in, it's in some weird frame. And now I do crossing. So now 2 crosses, so it points that in the other direction, and 3 also crosses. So I end up with this diagram, but this is the T-channel center of mass frame. So this is 1, 3 going to 2, 4. And if now I can, so now in terms of equations, the first step gives you some Wigner-D matrices. So I start with the center of mass frame. So on the left-hand side, I have these the S-channel amplitude as a function of Mandelstam invariants. Then I did a boost, and I get some Wigner-D matrices. So these are the Wigner small d matrices because I just need to do a boost in the xz plane. So I don't get the full Wigner-D matrix. I just get a special case of it. And I end up in some weird frame for the 1, 2 goes to 3, 4 process. Then in the second step, I'm crossing. Once I cross, I end up in the T-channel center of mass frame. So I end up with some functions of Mandelstam invariants. So now I can just combine these two, and I get the crossing equation for the for the functions of Mandelstam invariants. And here I restored the argument, so it's just a function of one angle and each, and these angles are going to be functions of the Mandelstam invariants and the masses. And again, there is another phase that appears, and this phase appears because while doing these computations, so these Wigner-D matrices are actually 4 pi periodic because you can have half integer spin. And while doing these computations, it's hard to keep track of that. So you might make some mistake, which is basically proportional to say -1 to the 2j1 or something like that. And as far as we know, the only way to fix this is, to fix it in this, like once you arrive here, to fix it is to actually do a perturbative computation. So just draw a tree level diagram, and then that will fix for you this phase. As far as we know, I think this is the simplest way. At least we couldn't find some other way to fix this phase. Okay, so that takes care of crossing. So we can do the same procedure for, so here we were crossing particles 2 and 3, but we can imagine crossing 1, 4 or any other combination, and that gives you various crossing equations. So now we want to consider unitarity. And for that, I have to introduce partial wave amplitudes. And first, let's introduce some shorthand notation for the center of mass frame states. So in the center of mass frame, the momenta are going to be, so the first particle is along some direction p, and the second particle is opposite that particle, I mean that momentum. And so we can just use p, theta, and phi. So p is the modulus of this momentum, and theta and phi are the angular coordinates as a shorthand notation for this state. In general, this two particle states are reducible. So we can decompose them into the Wigner reps that we introduced. And since we are considering states with total 3 momentum equals 0, the Wigner reps will have 0, 3 momentum. Then by considering, we can deduce these Clebsch-Gordon coefficients by just from group theory. So we get, so this takes care of the transformation property, and there is some normalization, which is fixed once you just choose the one particle normalization and choose the normalization of your Wigner reps. And in particular, we are interested in the special case where the incoming particles are aligned along the z-axis. So that's theta equals 0 and phi equals 0. And the outgoing particles are aligned along this angle theta with respect to the z-axis. So this formula simplifies, and you once again get this Wigner, the small d matrix. And once you have this, you define partial wave amplitudes as just the matrix element of the t amplitude, the t operator in between these two particle Wigner reps. So the physical meaning of this Wigner, like two particle Wigner reps, is that you're taking two particles, say with helicities lambda1 and lambda2 in the center of mass frame, and then you're rotating them around each other so that they have some total spin L. And then the state has some helicity lambda along the direction P. And you define partial wave amplitude as just as I mentioned, the matrix element in these states. Then just from using this decomposition, the partial wave decomposition just follows straightforwardly. So you just get this Wigner D matrix, and there is some normalization constant that just, normalization factor that comes from the expression for these CL of P. And one other point is that, right, so this expression is for identical mass, for identical particles. For non-identical particles, you can write an expression as well, but it's more cumbersome. So I just displayed the formula for the identical particles case. So once we have that, we can now set up the unitarity equations. So what we do is that we consider both all possible states which we can make of some total angular momentum L from the incoming particles and the outgoing particles. So for the helicity lambda1, I have various options. I have J1, I can take J1 minus 1, etc. until minus J1. Similarly, for the second particle, I can choose J2, J2 minus 1, and so on until minus J2. So the number of such states I can make is 2J1 plus 1 times 2J2 plus 1. Similarly, for the outgoing particles, I can make all these various, I can make all these various combinations, and I get this number. And then unitarity is just a statement that no matter what linear combination I make of these states, it must have positive inner product, which means that if I just take the inner product of all these states and make a matrix out of it, it should be positive semi-definite. So I just take in states with in states with out states, and also the out states with in states and out states with out states. And this must be positive definite. Now the in states with in states and the out states with out states are just normalization. So it's just, we're going to just think of them as, say, identity. The in ket going to out bra is basically the S matrix element, whereas the out ket going to in bra is the S dagger element. So basically you get a schematic equation of this form, where this S operator matrix elements are related to the partial waves we introduced by this relation. So once again, there is this free propagation piece, and you get the partial wave amplitude. So you just compute the various partial wave amplitudes you can have, and then you will so this matrix will be 2j1 plus 1 times 2j2 plus 1 times 2j3 plus 1 times 2j4 plus 1. So it has all the partial wave amplitudes in some wave based on how you arrange your states, and this whole matrix should be positive definite. So now we can, in principle, try to do some, yeah, we can put this on a computer. So this was the general, the formalism for general spin. So all of these steps, they work for particles of any spin and any mass. So now we would like to apply it to to the special case of Majorana fermions. But before that, are there any questions?
So I have a question. So you have crossing relates the amplitudes to the amplitudes for antiparticles. So
yeah.
So you have to impose that the particle is identical to its own antiparticle to get some mileage out of this crossing, or
yeah,
not
or you will
necessarily?
have to consider both the processes, right? I can consider, say, 1, 2 goes to 3, 4, and I can also consider this all the crossed processes, and then I can just think of all of them together, and I get some gigantic unitarity condition. So basically, I have to make sure that it closes.
So basically, if the particle is not its own antiparticle, you have to add both of them among the list of the. Okay.
Yeah, exactly. Yeah. Here we kept it simple, and that's why we considered Majorana fermions. So it's its own antiparticle. So we don't have to worry about this.
Mm-hmm. Sounds good. Thanks.
Okay. So now, yeah, we want to consider scattering of identical Majorana fermions. So a priori, we have 16 amplitudes because, okay, it's spin half. So it's 2 to the 4. Now, first of all, there is Fermi antisymmetry. So I can just interchange the incoming particles and also the outgoing particles. This keeps ST and U fixed. And basically, this imposes the following constraint on the scattering amplitude. Then what I can do, since the particles are their own antiparticle, is that I can cross 2 and 3 and then cross 1 and 4. And this will also keep ST and U fixed. And this will lead to this additional constraint. And basically, by using these two relations, the number of independent amplitude reduces to 7. And this matches the counting that was found in 3D CFT. So there is this idea that the counting in 3D CFT should match the counting for scattering amplitudes in 4D QFTs. So yeah, so that explicitly works out here. In addition, we can impose parity. So I didn't have time to cover how to tackle parity for the scattering amplitude. But basically what happens is that, so first of all, you see that the helicities change sign. And this is because, as I mentioned, the one particle states, the helicity changes sign. In addition, when you do parity, you actually go out of the center of mass frame because the particle 1, which was along positive z-axis, now goes to, say, minus z-axis. So you actually have to do a rotation to bring it back to the center of mass frame. And that rotation keeps the helicities unchanged. As I mentioned, rotations don't change helicities, but it just does cost you a phase. And that phase is precisely the phase over here. But yeah, unfortunately, I won't have time to show exactly how to get this phase. But yeah, so this is some phase that comes from that computation. And if you impose parity, it further reduces the number of parity invariance. It further reduces the number of independent amplitudes to 5. And this also matches the counting in 3D CFTs. So now we have these relations, and using that, we can reduce from all these 16 amplitudes to 5. And we choose this set of 5 amplitudes. So here the plus is signed for plus half helicity, and the minus stands for minus half helicity. And so we choose these 5. And we had the general crossing equation. And now I can consider the crossing equation for these 5 amplitudes. And it's going to be a 5 by 5 matrix, and I have it here. And as you can see, it's an explicit, as you can see, it's a function of S and T and the mass. And similarly, you can also compute the SU crossing matrix, and it's also going to be some function of the Mandelstam invariants. Now I'll just try to briefly talk about kinematic singularities. So basically, I didn't talk about the explicit definition of the states, but the idea of how we define these states is that you define them in their rest frame where they have 0, 3 momentum, and then you boost them along the z-axis and then rotate them to their final direction. And this is important for us if you want to consider kinematic singularities. So basically, for example, consider particle 3. It's at an angle theta with respect to the z-axis. So to get this state, you have to start in the rest frame for this particle. You have to boost along the z-axis by some rapidity, and then you have to rotate by this angle theta. And the issue is that this parameter, this angle theta and the rapidity eta are related to the Mandelstam variables through these equations. And as I mentioned before, this relation has some non-analyticities. So at t equals 0, s equals 0, and s equals 4m squared. Then using some algebra, which is a lot of technical details, you can isolate the behavior at these special points. So I won't show that computation, but the final result is that at this point, s equals 4m squared, the 5 amplitudes that I defined have this pole, and these residues are further constrained. They're not just independent. They're all related to each other. In addition, at s equals 0, the first 4 amplitudes are fine, but the 5th amplitude has a square root branch cut. And similarly, at t equals 0 and u equals 0. So now what we can do is since we know the precise behavior, we can define new regularized amplitudes, which don't have these non-analyticities. So I just make some linear combinations out of the amplitudes multiplied by this s minus 4m squared. For the 5th amplitude, I also cancel out the branch cuts. And so I define some new amplitudes called regularized amplitudes, which are basically some linear combinations of the 5 amplitudes. And this matrix M has all these factors and some in some way so that, okay, you get some amplitude, regularized amplitude. Now you have some new objects called these regularized amplitudes, and we want to think about, so we want to use these as our objects for Bootstrap. So we say that since we removed the kinematic singularities, all remaining singularities have to come from physical reasons, so lambda analyticity. So we basically say that, okay, they can have some bound state poles, and they have some cut starting from 4m squared up to infinity. So we use the same idea that was used for the scalar Bootstrap. We make this row series ansatz. We map the cut ST and U planes to the inside of a disk, and the top of the branch cut is mapped to the top of the disk, and the bottom of the branch cut is mapped to the bottom of the disk. And this is our ansatz for the amplitude, and this takes care of the analyticity properties. To actually work with it in practice, we have to cut off this series at some nmax, and then we vary this nmax and look and see the convergence to get some actual bounds. And the idea is that as you increase nmax, you're giving the function a lot of freedom to attain the optimal function. We now want to consider crossing for these regularized amplitudes. And since we know the crossing for the amplitudes, like the helicity amplitudes, I can just conjugate the crossing matrix that we determined with the matrix M that we used to go between the helicity amplitudes and these regularized amplitudes. And if you do that, it turns out that this crossing matrix is purely numerical. And this is very nice because now this is just these are just linear constraints on our coefficients, the coefficients in this series here. I just, so this crossing matrix is just going to impose some linear constraints on the coefficients, which we can solve.
Question?
Yeah.
Is this like a big coincidence, or does it have to work for every amplitude, every spin, the fact that then the crossing matrix becomes numerical?
Yeah, I don't think it's a coincidence because I'll now show there is another way actually to get this crossing matrix also. So that will probably answer your question.
Okay, thanks.
Okay, and similar thing happens for SU crossing as well. So now we have been talking about this way to do it, which is this center of mass frame amplitudes, then remove singularities and so on. But I also mentioned the other option, which was through tensor structures. So for the case of Majorana fermions, for example, like I can choose some tensor structure, some 5 tensor structures as shown here. So here the U and V are the familiar solutions to Dirac equation. And you just contract them in some way, and to get the different tensor structures, you put in some, so here you just have identity, here you put this gamma matrix, here you put the sigma matrix, which is basically the commutator of the gamma matrix, and then you make some gamma 5 gamma here and just gamma 5. So these are your 5 structures. And then it basically the regularized amplitudes that we define are exactly the scalar components that sit in front of the tensor structures. I mean, this happened because we had some freedom in choosing the matrix that takes us from helicity amplitudes to the regularized amplitudes. And for the choice of that matrix, for a particular choice of that matrix, you end up with this fact. And now, since we have tensor structures, we can also derive crossing in another way. Okay, I mean, first of all, what I wanted to say was that this matrix M that takes you from helicity amplitudes to regularized amplitudes, it's just, you just go to take the tensor structures and you evaluate them in the center of mass frame. And that's it, that's going to be exactly this matrix M. To get crossing, what you have to do is you have to consider these Dirac spinners, which are normally defined for positive energy momentum. But since you have explicit expressions for them, you can analytically continue them to negative energies. And it turns out that, you get some factor of I, but as expected, the helicity flips, and also the U spinner becomes V spinner. So U spinner you can think of as like for the incoming fermion, and V for like the outgoing fermion. So you can use this along with Fier's identities to say that the cross tensor structure, to show that the cross tensor structure is basically the uncrossed tensor structure, but with some matrix C. And this matrix is precisely the numerical matrix that we had. And so maybe, yeah, I guess this answers Marco's question. So in general, I mean, we didn't check because this constructing these tensor structures for general spin is a bit of a pain, because you can construct many structures, and then there will be many relations between them, and then you have to figure out how to, so it's a bit of an art. You have to figure out what is an independent set, and then how to relate after you cross back to this independent set. So that's why we didn't try to do this for the general case. But in this special case of Majorana fermions, for example, this was also quite well known, this relation here. And so here, yeah, I would say, yeah, in general also, I'd expect that these crossing matrices are going to be numerical, but okay.
Sorry, can I add questions to Marco's previous question? So yeah. Wouldn't you get this relation essentially directly from the LSG, putting together?
No, but if you do, yeah, so you're saying, okay, you do the LSZ. Okay.
LSZ with arbitrary polarizations, and then you repackage in a way you use crossing as usual.
You still have to consider some basis of these independent tensor structures, right? What you're saying will give the relation between the generalized helicity amplitudes. That LSE will give you that directly. But then when so now if I want to consider center of mass frame amplitudes, I have to consider some basis, right? And this LSE will not give you, you'll have to use Fiat-Pauli like identities, but for higher spin these polar, higher spin such solutions to get this crossing matrix. I don't think LSE gives that.
No, I mean, okay, never mind. I mean, LSZ is going to give you not on the basis you want. Then you have to go to that basis. I agree.
Exactly.
But,
yeah.
But okay. Anyhow, okay.
Yeah.
Thanks.
Okay. So this is so this was crossing, and now finally we have to implement unitarity. So a priori we can make 4 states out of 4 of these Wigner-Irrep 2-particle Wigner-Irrep states out of Majorana fermions. But since they are identical, whether I have first particle having plus helicity and my second particle having minus helicity or vice versa, it's the same because they're identical. So once you make this total, this state of total angular momentum, it doesn't matter which one, you can't distinguish them. So you don't need to consider the first state. It's just going to be the same as the third state. In addition, we can make some combinations of the other 2 states such that they are eigenstates of parity. So as I mentioned, parity flips the helicity. So if you have first particle with helicity plus and second particle with helicity plus, it will flip it to minus minus. So you make 2 linear combinations out of them, which are going to be parity eigenstates. The particular combinations we have made: state 1 is parity odd, state 2 and 3 are parity even. And in addition, because these are identical particles, there are going to be some selection rules. You can make these states only for even L. And this third state you can only make for L greater than 1, because if you have L equal, you cannot have spin L being lesser than the helicity difference. So you can't have spin L equals 0 while the helicity difference is 1. So you have these selection rules. And now, since we also apply parity invariance, state 1 cannot transition into states 2 and 3. So the unitarity matrix is going to decompose into submatrices. And these inner products that we are considering, so we have to take state 1 as an incoming state with state 1 as an outgoing state, and so on. So we have all these combinations, and these are related to the partial waves in this manner. And okay, this normalization I didn't talk about, but if you're careful, you get these factors. And once you have that, you can write the final unitarity conditions. So you see that most of them are just going to look similar to the scalar case. You have to make some combination and you get some just like one component essentially. It's phi1 plus phi2 here, phi1 minus phi2 here, just phi3 here. But there is this one 2x2 block, which comes from the fact that state 2 can transition to state 3 and vice versa. So you get this 2x2 block, and that has all these amplitudes. And in practice, what we do is we impose these unitarity condition up to some L max. And again, the idea is that as you increase L max, this is going to be stronger constraints on your ansatz. So the bound you get will be better and better. So we look for convergence in this L max. Okay, so now we have the constraints on the amplitudes set up. So we look for some targets to optimize. So one target is what we can call the non-perturbative definition of the quartic coupling. So what we do is consider the crossing symmetric point, which is S, T, and U all being 4m squared. Now at this point, this regularized amplitude must be a simultaneous eigenvector of both ST crossing and SU crossing, because I cross, it just goes back to the same point. And this condition has just one solution, and it has to be of this form, where lambda is some free parameter. And if you have some interaction, which is this psi bar phi type interaction in perturbation theory, it gives exactly this term in at tree level. And so now this lambda is a target that we can optimize. And basically for the upper bound, we find these, I mean, for the upper bound, we have this plot. So here the red dots are n max, and we go from 10 to around 26. And each time we keep L max to be around 20 more than N max. And we found that this is enough to get some good convergence in L max. And we can fit, try to fit to the last few points where it seems to be converging well and extrapolate to high N max. And we found some bound, which is around 2.7. Similarly, we can also consider the lower bound, and it's the same. And we found some bound which was around -11. Now that was the quartic coupling. Now we can also imagine adding a bound state to our problem. And we consider the simple case where it's the bound state has spin 0. So it's a scalar particle. And how we impose that is that, so we add some poles to the scattering amplitude. And then we demand that the S channel pole that we added should only contribute to spin 0 partial waves, because if it contributes to any other partial wave, it's not just a spin 0 particle. And this leads to two solutions. The first, I write here the expression for the regularized amplitude. And the first solution looks this way. And this, in spin 0, we actually have two different partial waves, and one combination is parity even and one combination is parity odd. And this term contributes to the parity even spin 0 partial wave. So we can identify it with the actual scalar bound state, a parity even scalar bound state. And indeed, if in your Lagrangian you add a term which is phi psi bar psi, then it gives rise to this term at tree level. And yeah, we can bound this coefficient g square as a function of the mass m of the bound state. So this mass m must be between the mass of the fermion and twice the mass of the fermion. And if you do that, you get these plots. So we did this for n max equals 12, 16, 20, and 24. And then, okay, convergence is not as nice as it was in the scalar case, but still we can extrapolate and get some bound. And in fact, this is one of the reasons why the dual formulation is an exciting prospect, because then we'd be bounding it from the other side. But okay, I'll talk more about that later. And as I mentioned, there are two solutions. The other solution corresponds to a pole in the spin 0 partial wave, but the parity odd combination. And so it corresponds to a pseudoscalar particle. And yes, interaction of the form phi bar, psi bar, gamma phi psi gives rise to such a term at tree level. And we can bound this coupling g square as a function of the mass as well. And that gives rise to this plot. In particular, what we can do is near the threshold, we can do some non-relativistic approximation and try to estimate what the bound will be. And for the pseudoscalar coupling, you get that it should basically go to 0. So so our numerics match this non-relativistic prediction. These are the bounds. And yeah, that was our exploration in the Majorana fermion case. And now I'll conclude. So basically, yeah, we reviewed and set up the formalism for bootstrapping particles of any spin. So most of it was well known. We just reviewed it and then cleaned up some things and then set it up in such a way that, okay, you have some pieces, you just put them together and now you can put it on a computer. We applied it to Majorana fermions. And now for the future, we have some interesting possibilities. So we can consider, for example, scattering of pion and nucleon. And now you see, this is a very interesting system, because by crossing, this is going to be related to the process where it's pion-pion going to nucleon-nucleon pair. And then when you want to consider unitarity, you will also have some cuts which come from pion-pion going to pion-pion And so there'll be a rich system of many different processes. And the upshot of all that is we get access to the deuteron bound state. And that is something that we can study by considering this pion nucleon scattering. Something else we can consider is scattering of spinning blue balls. Yeah, so, and in principle compare with lattice. There is also, in this whole talk, I was just considering massive particles, but in principle, many of these things, you can take the massless limit, and you can also consider massless particles. And in particular, we can consider, say, photon-photon scattering, where you do not have these usual IR divergences because photon interactions are soft in the IR. And this is some work in progress. And what we hope to do is place some bounds on Wilson coefficients in the low energy effective field theory. And one thing that would be exciting is right now there is a dual formulation for S-matrix bootstrap in 2D. But if there is a dual formulation in 4D, it would be nice to have it also for spinning particles, where there is need for it, because the convergence seems to be difficult in the way we do it, because it's, so the way we do it is the primal approach. We try to construct S matrices that are allowed, and then we try to push it as much as possible and say, okay, we pushed it as much as we could with the really general ansatz, and this is probably the best that is possible. But with the dual formulation, you start ruling out S matrices. You say, no, this S matrix is not allowed. So you're actually placing bounds from the other side. And it also seems that in 2D, at least, the dual formulation converges much faster, and it's also numerically less intensive. So it would be nice to have a dual formulation of what we are doing here. And yeah, that's it. Thanks for listening.
Thank you, Aditya. So, other questions?
Me? Perhaps I'll ask another question. I'm still a bit confused about kinematic singularities.
Yeah.
In particular, are these things? So when the formula with H and the tensor structure was also good. But anyway, so
which where, do you want this or this?
I'll just ask you a question, then you'll pick the formula, which is best.
Okay.
This singularity seems to arise for some reason which depends on parameterization, etc. What I did not understand is there's, when you choose for H to be regular, meaning that then you expand it in a regular expansion. Taylor expansion. You're forcing the T's to have these singularities. Because the tensor structures have them, right? So you had some.
Yeah.
And so is this physical? So the amplitudes should have the singularities at say S = 4m squared, or not?
I mean, the amplitudes should have these. But if by amplitudes you mean these amplitudes T of STU, if that's what you mean, then yeah, they should. You can
I mean the overlap of in and out states, right?
Yeah, but when you consider them as functions of Mandelstam invariants, yeah, they should have it, as in these are there for any spinning particles. And one way indeed to think about them is that, I mean, okay, we don't, at least for the spinning case, it works out. So if you see these tensor structures are written for generic momenta, I can also write them, go to the center of mass frame and write them in terms of ST and U. And then indeed, these contain the kinematic singularities. But what, I mean, I don't know if this is obvious, but I don't know if this, I mean, we suspect this is true, that for even higher spin, this is the case, that the tensor structures basically have the singularities. And so this, whatever you have will be the regularized amplitude.
And I guess I like to understand if there is a physical way to understand why the amplitude should have this this kind of, let's say there were singularities in this formula set S equal 4m square, right, for instance. So
yeah, so
and these are very specific. So this in this non-relativistic limit, what happens that gives the amplitude this divergence, for instance?
Yeah, I mean one thing. So I don't know what you mean physically, because these are basically, as I was saying, kinematics, right? Here, I mean, the way at least I understood them was that you see, you are trying to describe these using some variables S and T, and it turns out that these are not good variables to use at these special points.
Okay.
Yeah, but there is a related phenomenon that's happening, which we were not quite able to figure out. Maybe Dennis has some more comments. I don't know if he's there actually, but it is that, so for example, at S equals 4m squared, all the particles are basically at rest. So you can see that there is some symmetry enhancement at that point, because there is some SO3 symmetry that is now there, which was not there for non-zero at S not equal to 4m squared. But and in CFTs, I believe that by considering this, you actually get some constraints. But here, at least the kinematic singularities don't seem to be related to that. The kinematic constraints, I think they are related to that fact, yeah.
Okay, yeah. So, but anyway, okay, thanks. I think I understood. So just the statement that when S goes to 4m squared, also T needs to go to 0. I mean, it's just, I see. Yeah. So there is no special singularity in the amplitude in the end. It's just a variable.
Aditya, maybe I can just add one comment.
Yeah.
If we define our physical amplitudes, we pick the domain of STU variables. And in the physical domains, there's no singularity whatsoever.
Yeah, exactly.
All in S minus 4m squared.
Yeah, you have to keep T not 0, which is not physical, yeah.
Right.
Yeah, thank you. Very good.
The problem appears that now you want to actually go outside of the physical domain, because you want to analytically continue it to the complex S and T plane. And when you do that, you generically treat S and T separately. And that's what you see, this singularity, this pole appears, and you also get branch points, T and U. But again, this is once you go outside of the physical domain.
Thank you.
And another statement, just to be concrete, that yes, these kinematic non-analyticities, they are present in the center of mass amplitude. They are always there.
Yeah.
Again, I ask refinement of Marco's question, maybe because it's the same name, I don't know. So,
well, I might ask a question in a minute, and then I'll go do something.
This non-analyticity that kinematic singularities resembles a lot similar non-analyticity that appears in the analog for fermion correlation function CFT, which Dennis knows very well. So I was wondering if there is some sort of it looks very much the same, but in that case, we understand them as points in which as special points in the conformal cross ratio, there is an enhancement of the stabilizer group of the conformal group. There is an enhancement, not from U1 to SO3, and then you have to demand that the amplitude is such that. So is there an analogous enhancement here? Can you comment?
Yeah, that's what I was just. I think maybe
probably I missed that. Sorry.
Yeah. Okay. So for example, at S equals 4m squared. So let's go to this formula here. So if we go to S equals 4m squared, you see that this momentum is 0, this momentum is 0, and all these momenta are also 0. So there is an enhancement to SO3 because now any rotation is sitting in.
Yeah. Sorry. Yeah. So, thanks.
So in the case of scattering of Majorana fermions, is there any global symmetry you can impose by regarding the Majorana fermions belonging to some representation of a global symmetry group?
Yeah, you can allow them to be in, say, some real representation, right? It's I
mean, what is the natural symmetry group in this case? For scalars, it would be ON, I guess. But,
yeah, but here, so why can't you do the same for Majorana fermions? Can it be SON or ON if you had multiple Majorana fermions?
In the case of scalars, going to ON doesn't increase the number in variance. It's just as simple as situation, more or less. Well, there is some extra problems, but
I don't think I understood the question then.
well, I was thinking of a more tractable problem with some additional global symmetry.
Okay, yeah, because here we don't consider any global symmetry at all, right? In this whole setup, it's just the same Majorana fermion. It's uncharged, there is no global symmetry. But you're saying you would like to consider some situation where these have some global symmetry, and there's some representation of this global symmetry.
Yeah, in an ideal world, the bootstrap should pick out some global symmetry or something like that.
Ah, okay. Yeah. Yeah, I'm not sure. At least in the way we're doing it right now, I don't think we see any of that. I mean, we have to impose some. We can, for example, generalize our setup and impose global symmetries, and then we can try to see what happens if we play around with this n, for example. But in the way we're doing it now, okay, I don't think we'll see it.
So I have a very simple question. So is it obvious that the spin 1/2 scattering has the same good analyticity structure that we expect from scalar one? So typically we expect spin appears somehow in the numerator of the amplitude, so shouldn't change the analyticity structure, very naively speaking, right? But I was wondering if we have some more rigorous axiomatic whatever proof that the analyticity is the maximum, some sort of maximal analyticity can make sense, and there are no subtleties. Modulo the one which I believe Slava was referring about Sasha. Okay, modulo that. Do you expect that?
Yeah, I think the idea is that again we can start considering these Landau diagrams, and then actually because you have spins, for example, some diagrams will actually not be allowed anymore because, for example, if you have a fermion, you can't go into two scalars, whereas if this was just a scalar, that would be allowed. So in that sense, you could even say, you could even naively expect some better properties, right? Because some diagrams are not even there, which could have given you singularities. But otherwise, in terms of rigorous statements, at least I'm not sure. So I don't know if Joao has any comments.
No, I agree. I like to take the pragmatic approach of looking at perturbative diagrams, and in perturbation theory, you will see that you always get functions of ST and U with usual properties times the tensor structures that Aditya showed. So that's the argument is perturbative.
Can I also add a comment to Slava's question and Marco's comment? So one should distinguish two things. One is the theoretical setup, namely the crossing equations and unitarity. And this is like purely theoretical. And the second one is how you implement it in a numerical fashion to get anything practical. So setup is complete, well, at least unitarity, what we do is completely rigorous. The question is, how do you just use it numerical? And that's where you can add things. So, yeah.
So to recall concretely what Sasha was saying, is that he was saying that the exact amplitude S satisfies this unitarity constraints. Now we replace this exact amplitude S by a certain series which converges to the amplitude in a certain sense for sure, but this convergence is expected to be rather weak on the boundary of of where the unitarity constraint is imposed. And so, you know, while the S matrix satisfies the constraint, since the convergence is not pointwise uniform on the boundary, it's not clear that the approximants to the S matrix are going to be satisfying the same constraints pointwise on the boundary. I mean, this seems to be a pretty simple idea, and I'm worried that there was some basically Sasha didn't say it explicitly in his talk, but in private he says that he just doesn't believe those published bounds. That period, those bounds are vacuous. Now you produce 4 bounds, but you kind of maybe you can tell what you think about what he said. Is it correct? Is this constraint correct, or is he just being
the word bounds is dangerous? Okay, in this paper we actually said we estimate bounds. Okay, of course we don't produce bounds, right? We construct amplitudes. I think what Sasha is saying is that our constraints are too restrictive, so there are other amplitudes which are not possible to approach within our ansatz, which have bigger couplings.
Yeah.
And that remains to be seen. It's true, that remains to be seen. I very much doubt, but it's true that it would be good if some new method, either the dual. So we have one example where there is a dual bound from the 70s, and it's very, very close to our primal bound.
But can you remind me the dual, because the dual the dual methods, the talks that I've seen, they were not very pedagogical compared to today's talk, at least. But I mean about high dimensional dual bonds. So those dual methods, are they free from Sasha's objection?
So the dual methods in higher dimensions, there is nothing published which is less than 40 years old.
Okay, but whatever is published,
there is the talk that Martin Kurczynski gave at the Bootstrap, which we are still waiting to see the results anxiously. And there is this paper from the 70s by Lopez and Menessier, where they implement a form of a dual S-matrix bootstrap. Even using only the analyticity that has been proven, they don't even use the full Mandelstam analyticity. And they obtain a bound for the problem of the quartic coupling of identical massive scalars, which is like 2.7 or something. And then we produced with our primal method 2.66 or something. And they do not claim to be optimal, right? We don't even, so Dennis with the master student last year reproduced some of their results, and this was rather non-trivial, Dennis can tell you. So it's even a bit mysterious how they actually found this dual bound and this optimal functional.
But when they act with this dual method, so when the dual method also has to be carefully analyzed in the light of Sasha's remarks, because in the dual method you act with a certain function on the S matrix and so on, and so at some point you probably have to commute some things with some things, and if the things do not converge, then you basically may be going down the same hole in a sense, in a dual, from the dual side. I don't know if you have a perspective on this.
Oh, but you're integrating, and if the exact amplitude obeys the bound, I think it should be safe, right? You're not approximating.
What are you integrating? Are you integrating a smooth kernel against the amplitude? Or are you integrating something?
I think it's a smooth kernel.
Okay.
Well, at least it's continuous. There was maybe one. The domain, there was 2 regions, right? But it was at least continuous.
Okay.
Yeah, I think it is continuous. And on top, I wanted to say that Sasha, I think what he proposed, instead of requiring a unitarity at each point, he basically says, let's integrate it with some, or smear it with some function and impose constraints of that. This is in principle easily implemented in our numerical procedure. We can do it. It's not, I think it's not a big deal, but it just was an extra thing to add. We would let Sasha probably to do it first in the scalar case and show us that it's worth it, and then we can add it to the spinning case.
Okay, here's some strong opinions. That's nice.
Relatedly, can I then ask? So if you were to parameterize, like in some earlier work, I guess, amplitude with discontinuity and then dispersion relations.
Yeah.
I guess that would bypass this comment because you're not Taylor expanding. You're just picking some spines. So you have some function for the discontinuity. I remember like you guys giving me comments about this is not optimal numerically, but can you expand on that?
Yeah, so Dennis was trying that, right? And I think even for the scalar case, I think, yeah, I guess Dennis was the one trying that.
Sorry, Marco, could you recap again the question?
It's
sorry.
you were trying the splines to, what's that, to parameterize this discontinuity and then trying to do that, right? And then we have, I don't recall what were the exact difficulties, but you might remember.
Okay, I can say a few words. So currently we use the raw expansion to parameterize our regularized amplitudes. And practically speaking is the best thing. But what is the difficulty? What is the main step here? Once you wrote the raw expansion, you have to produce partial amplitudes. So you have to integrate with your Legendre polynomials, or in the spinning case with the Wigner-D matrices. And these integrals are complicated, and we perform them numerically with Mathematica. When we get to the splines, it's a little bit more complicated because you basically parameterize the double discontinuity. It's okay, but then you have to perform these integrals numerically. And well, it's still doable. But then there was an extra issue that these ansatz we wrote did not converge properly. So basically, we had some very strong oscillations.
So this we observed numerically, but this was something that was partially explained by Martin in his talk in the Bootstrap, which so apparently what happens is that when you go from the double discontinuity to the amplitude, when you integrate, it's kind of it's a kernel that you integrate, and this kernel, how is it? It has a kernel. Sorry, this integral kernel has a kernel. So there is a part of the double discontinuity that integrates to nothing. It's like integrating. He was doing the analogy with integrating the diffusion equation backwards in time, and like high frequency modes are not. You cannot predict what happens. So that's one of the things that we are also waiting to see the paper. So he somehow came up with a way to regulate this by adding some norm to the double discontinuity and then studying as a function of the norm. And it worked for him in the end. He showed us pictures converging with the double discontinuity. But there is a non-trivial conceptual problem there that I think he understood.
Thanks.
Why is there not in your list the scattering of pions in the to-do list? You don't see any way to, well, of course it's still scalar particles, but you don't see any way to improve on what has been done already?
No, pions, it was done, I believe, no?
Well, I mean, done, but
what
is done does not solve the problem. Does it mean that it's not doable with this method? You cannot.
No, with the S matrix bootstrap itself, Joao, Pedro, and Andrea have, I think they were doing so Joao.
Sorry?
But what do you mean, Slava? Pure pion scattering, we did already the massive bootstrap, and a few weeks ago we did the massless bootstrap. I think if just pions, well, we could also
have I missed your paper? I'm sorry. That would be really embarrassing.
No, it's okay. There's lots of papers every day on the archive. It's okay.
Yeah, but basically in this talk,
okay, I take it back. I don't know how I missed it. Sorry, guys.
We do not improve on the numerical side. We improve only on the spinning side. the theoretical side. We cannot add anything to pions. Joao knows everything.
Yeah, so massless pions, I guess the thing that would be also useful, that is the dual formulation. Of course, the dual formulation would help all problems. Apart from that, I think the next step to really get more about QCD would be to do the joint system of pion and nucleon, like Aditya was explaining.
But isn't this hyper complicated, because you will have in the cross channel, you have a ton of bind states. There's going to be all the resonances, intermediate resonance. The nucleons are so heavy. What are you going to do about omega, rho, all this shit in the middle?
Well, that we don't care, right? Everything that is a resonance, it's not an asymptotic state, so
so it won't come in this unitarity equations.
We hope it becomes a bump. In for example, in the pions, we do see resonances appearing, like the rho meson. We don't put it in. We see that at some regions of the boundary, resonances appear in the optimalized matrices. So I guess one has to try, but it's not going to complicate the framework from the start. It's just some mixed amplitude system where you have to do pion pi goes to nucleon, and then nucleon. It's okay. It's big, but I think it's not really unfeasible at the moment. It's probably manageable.
Okay. Sounds great.
Yeah, and also this would be an example related to the question you were asking, right? You were saying what happens if they're not their own antiparticles. So in this system, you would have nucleon going to nucleon. Then if you cross, it will be nucleon bar going to nucleon bar. So it will be sort of what you were asking about.
Looks like we're done. All right. Thanks again for the talk. See everyone.
Yeah.